Hi guys, thank you so much for joining our last stream in 2022, which is crazy. I think we can start. If anyone was attending our last stream, welcome back. If you are here for the first time, thank you so much for joining. Hopefully, we will see you in 2023. My name is Anya. I'm a business development manager of Kmine, and if you haven't already, please follow our LinkedIn page where we post our announcements for the future streams. So today we will talk about resource modeling and strategic planning in Kmine, and more specifically, how to create a strategic planning database and solve strategic tasks. So if we go over our agenda, we will see that after reviewing the full work cycle, we will see how to work with geological information, including the block model, and what would include things like how to create a block model in Kmine, how to work with the database, and how to apply geostatistical analysis, creating wireframes and filling up the block model. After the block model will be prepared, we will see how to prepare the data for strategic planning. And after that, we will show you how to determine the optimal parameters for strategic plan that would provide a good economic conditions. And in the end, we will define optimal contours, and we will divide the final pit into pushbacks. So it's a lot of house today. For people that join our webinar for the very first time, I just want to talk about some highlights of Kmine and what we do, what we are about. We are a mining software company that has been on the market for almost 30 years. We provide one standalone application that is customizable and adaptable for each company's needs. That allows us basically to work with a company of any size and provide them with a reasonable pricing, because our solution is model-based. The application is based on its own patterned graphic core, and that core processes information way faster and is proven to provide more precise calculation and estimation when it comes to, let's say, resource estimation, or let's say how many explosives and charges you need. Overall, we aim to cover the most operational needs, such as 3D modeling, resource estimation, planning, equipment management, and so on. So what does it mean specifically? Today we built 12 models for open pit and underground mine. Each of this model can be configured, adjusted, enhanced for each deposit, and because basically the company business model is based on the policy of maximized optimization and ultimate belief that software should be designed around the company and its needs, not vice versa. Our engineers not only set up the whole company infrastructure during the implementation of our solution, but also assist our clients at any stage of work, creating 3D models, planning schedules, estimating resources and reserves. And each of these 12 models can be used as a standalone module, or they can use in conjunction with each other. So you can basically pick whatever models you would like that would cover your workflow, and that will be the models that you will use, or you can use just one model if you want. And that allows us basically to create one digital space where all geologists, mining engineers, surveyors can work together, exchanging information, receiving real-time data from the site. The company offers specialists that the ability to edit their calculations, and they can change anything at any time. And this way, mining managers and directors can get an up-to-date summary of the situation on the mine and make decisions faster when it comes to the changes on the site or on the market. We also offer custom solutions when we integrate upon the request, because not everyone needs it, but especially for corporations, they need end-to-end mine planning, where they basically have to follow the value chain from the moment you start mining until the moment the product hits the market. You can have it split per shift, per day, plan the load distribution on the equipment, and many other parts of the process. The other new solution that we released is IoT platform, and that works as a web-based interface. And this way, this is kind of like a game changer for the top management of the company, because basically the solution transmits real-time information from IoT devices and personnel, and can display gas consumption information, can track location of the equipment and personnel, create a dashboard based on this information, and this analytics, this reports are complemented by historical data. And so the company C-level management can receive heat maps about where employees have the most frequent problems, when equipment needs maintenance, etc. So all this information will help managers get real-time reports and solve the problems efficiently and on time. And the other custom solutions are integrations with OpenPit and Dispatch systems. Basically, these integrations allow to obtain and visualize information from dispatch systems. And I will talk about it in more details a little bit later. But basically, it's for various services, and it helps engineers to operate their mine successfully and manage equipment for the open pit or underground mining. So that being said, the integration with the different equipment also has to do with this surveying equipment. So it's like kind of like one of the areas that we improve on a daily basis. Our goal to create kind of like the most simple and automated way to gather data from the deposit, so that people will not have to deal with papers or with the bunch of other reports in Excel. And in one of our customized solutions, we integrated with different dispatch and fleet management systems like Wenco, Mindstar, ACK, Modular, and Caterpillar. And basically, in terms of integration, we actually basically can integrate with any system that provides us information that we can receive and import it in our application. So we basically allow our customers to manage all of the mining processes inside of one interface. So today, our software also allows us to evaluate projects, creating digital twins, creating life of mine, calculate resources, and all of our modules were based on the real use cases and projects than just theoretical knowledge. Our idea that the best way to enhance the product is when you do consulting work, because that's when you face challenges of the project, and that's when you kind of like know exactly what you need to add into your tools in order to speed up your work. And that's why we offer different types of services, since we have a lot of mining engineers, geologists, planners, surveyors, and other professionals in our staff. So, all right, so let's start with the theme of today's webinar, and let's figure out first where it all begins. Regardless of what type of deposit is to be mined, first we need to do a sufficient geological study. Based on this information, we will do the first calculations of the profitability of further exploration, and we choose a mining method and so on. But the geologists, they can use like specialized software, can be ours, can be anything else, but geologist creates a database, and then using implicit or explicit modeling interprets the mineralization zones and contours of ore bodies. Then a geostatistical analysis is performed and 3D model is created. At this stage, we make a decision about the size of block model blocks and a list of its attributes. So this way, a resource block model is created, and we can use it to evaluate the mineral resources and reserves of the deposit. So K-Mine implements algorithms that can be conveniently working with relational databases. There is statistical analysis, a built-in set of formulas, and logical expression for calculations, and also a wide range of tools for visualization and analysis of samples in space. We also do explicit and implicit modeling. So there are various options for ore bodies contouring that you can use. For example, in one case, it's possible to interpolate the gradient blocks and determine the boundaries of ore bodies with a host rock if there are no clear geological or lithological conflicts. If there are lithological conclusions and selections of tectonic composition, it will be appropriate to use the explicit method. So at the model creation stage, it's important to understand what the block model will be used for, what tasks you plan to solve with it. For example, operational planning or design of mining operation, or for performing geological, structural, technological mapping, or stability analysis of the rock mass. Filling with the block model attributes will be completely different in each of these cases. Also, at the stage of creating model, we need to choose the size of blocks, and it's very important. Today, using the example of a graphite deposit, we will see how the qualitative and quantitative indicators of the model change when the block size changes. We will also show how to process the subblocking is performed in K-mine, and vice versa, reblocking to larger block sizes and bringing them to the same size, which would be regularization. So let's talk now what follows the process after we completed the full range of work on geological surveys. So what's happening is it's engineering work follows this stage. First of all, you need to decide on the method of extraction, whether it's open pit or underground. The easiest way, if the solution is not obvious, is to measure the profit between two mining methods. And for this, you need to complete two projects. Also, what is not uncommon is a combined method when a deposit is developed by an open method and then is refined by an underground method. This is a part of strategic planning. And then when the method was decided, we can create a project called Life of Mine. It contains information about optimal contour, about pushbacks, and also approximate calendar, of course, and financial opportunities in general. That being said, it's important to have this general calendar because it's possible to move on the next stage of the planning, which is called midterm planning. And at this stage, the questions like where to dig or how much to dig are reviewed in more detail. And of course, we need to have a more clear understanding of the processes and equipment in this stage. But the information from the midterm planning in forms of like graphs, wireframes, lines, and other things will pass to the short-term planning section. The guiding principle would be the specification of the place and volume for the subsequent detailing of the processes. So the short-term planning is the most time-consuming process since it is necessary to take into account so many factors that influence successful implementation of the planning. And the last step of the planning is the operational planning. This type is characterized by the fact that, as a rule, it is carried out not by planners, but by dispatchers, by mining foremen and personnel that is responsible for successful work over the specific shift. So they take directives from short-term planning and they try to follow established plan as much as possible with adoption of operational decisions on the ground. So, of course, the results of a good plan and its execution of the analysis of the mining plan, which will be the plan compliance or reconciliation. So let's review each stage in more detail. The first stage of mine planning is strategic mine plan. The main target for this stage is to define the optimal mine strategy. In the processes of strategic planning, we need to get answers to questions like, what are the main or secondary goals of the company and how to achieve these goals? And what are the obstacles on the way to this goal? And in the end, what is the strategy to achieve these goals, right? Also, talking about maximum profitability, what would be the conditions for that and what would be the factors that affect this profitability? The most important output of strategic planning is life of mine plan. And we can get different scenarios of it. For example, we can get a scenario with very low investment, and usually what it means is production rates will be reduced. Then we can review scenario with a maximum investment, or the scenario where we just keep mining as usual. The most critical thing to strategic mine planning is the input, because the poor quality data can lead to very misleading conclusions if it was not spotted during the evaluation process. The most important and at the same time the most dangerous data in mining optimization is geology and how it will be processed at the stage of mineral processing. If geology and refining data are wrong, the whole optimization goes wrong, and doesn't matter how accurate the other parameters are, these are the most important things. And that's why the geological information that was provided during the mine optimization process must be as transparent as possible, and also it should be verified by more than one qualified geologist. Other parameters that are used for optimization are pretty simple because they are basically technical and economical parameters. We will break it down. If we would break it down to the set of rules of successful optimization, there will be around 10 of these rules. And the first rule of this process is that the objectives of the process of the project must be understood and communicated to the entire project team that is involved in strategy development business. And the second rule is to correctly evaluate geology and processing. Just don't make any assumptions, just evaluate it correctly. And then you have to double check your metal price estimates and operating cost estimates. Better double check them with someone else. Always evaluate multiple scenarios, always develop alternative strategies. Don't look only at profitability, but also at the consequences at the scenario. So you can analyze them, report them. And the other rule from that would be to plan mining according to mineral processing, because in the end, optimized production scenarios can significantly increase the NPV of your project. From the technical perspective, you can assess cutoff grade using marginal, operational, or break-even cutoff grade. And remember that ore and dilution, or dilution and ore waste are basically your hidden enemies in this process. As general rule, also remember properly sized mine will always increase the value and success of your project. And remember to cross-check your results using different approaches, very good software. Again, it might be K-Mine, it might be something else, but K-Mine. And remember that a single road at the top of an ore body won't necessarily ruin your project, but a natural preserve can. So we're moving on to medium-term planning or tactical planning, which usually is less labor-intensive because, as a rule, at this stage of planning, strategic issues are not resolved, but they are somewhat guiding direction. So midterm planning is usually 5 years, but it can be up to 10 years, and intervals can be split by years. The main task here is to study these areas, detail them, and develop a mining calendar for the midterm planning. To make sure that the plan follows the intended direction, you can additionally calculate the economic information about the cash flows in the planned time periods. Overall, during this stage, you should understand where to mine and when each mining block should be mined, and what is the sequence of the mining, and what do you need to reach that specific target. So the next planning is short-term planning, and it's the most time-consuming process because you need to account for so many factors that affect planning of mining operations. Usually short-term planning is not more than 2 years, and it could be split by weeks, months, or quarters, or years. And the main goal of this planning is to provide the most accurate mining sequences on the site. So that means it should be clear who, when, and what is required for each shift. Very often you also need to take into consideration schedule of run of mine, maintenance, drill and blast, stockpile balance, processing plan feeding schedule, and other factors. During this stage, the main strategic requirements and defined mining sequences are static, and they should be followed according to the previous stages of mining. After this stage, you will basically get the maximum clarity, because basically you will analyze the entire implementation of the mining plan, and the analysis then can be taken to other departments for in-depth analysis, and those guys should review the factors that must be taken into account if they want to approve the plan. So the next type of planning is operational planning, and it's kind of like the most emotionally intense and responsible, because you need to make a decision on the spot. No plan can foresee all possible scenarios, because we would always have the human factor, and that's why the implementation of the plan as a whole depends if you made a decision on the spot correctly. Like, no pressure, but this decision usually depends on the qualification of the person in charge, and if he can make this decision based on the strategic goals of the company. So the operative planning usually means it's up to 14 days, and it could be split by shifts. That being said, the operational planning involves the accurate coordination of the mining activities on the site, which includes plan compliance and equipment control in real time. And as well, during this planning, the main strategic requirements and defined mining sequences are static, so they should be followed according to the previous stages of planning. So now let's take a look at the example of graphic ore deposit and how the resource model is created. This deposit is mainly represented by biotite garnet and biotite graphite gneisses. So we have already created a database with a table of the results of drill hole core testing for the content of graphite in the ore. K-Mine has developed a flexible toolkit to visualize sampling data in space. So users can show the sampling intervals as text values, as a content curve graph, as a histogram, and users also can change their ratio settings and color palette for the visualization. Samples also can be shown on the screen as cylinders of different diameters, and it really depends on the value of the content in the sample. It's also very convenient to filter lithological varieties in the table, and by taking this filter into account, visualize individual intervals by drill hole. So for example, if we want to analyze the spatial position of biotite graphite gneisses, using this filter in assay table, we can predict the contours of biotite graphite gneisses domain using implicit modeling. Yeah, so here you can see that we would use implicit modeling to predict contours of the biotite graphite gneiss domain. So if we talk about a modern mining company, in order to be successful, it should have a good quality management strategy. Mine planning is directly related to block modeling as a method of determining the content of a useful component at any point in space. And it should select an elementary block that will meet a given condition. The use of the block model makes it possible to work with smaller blocks than with the polygonal method of calculating reserves, which in return makes it possible to more reliably assess the localization of poor and rich ores. This is happening because of the fact that the counting block in the polygonal method can contain ore reserves for several years of the mining, and the size of the block model corresponds to the size of the mining block, which allows more accurate mine planning. So in K-Mine, users can at any time change the minimum block size and perform subblocking, which basically means splitting a block into smaller blocks, and vice versa, reblocking, which is enlarging the block size of the block model. For example, when creating a block model, the minimum block size along the X and Y axis was 60 meters. To reblock the model, you just need to select the original model and specify the new minimum size of cubes in the block size field and save the file with a new name. This way, you can store several block models in the current project at the same time, which is convenient if you do a comparative analysis of the model parameters. Users also can do sub-blocking both for the entire model, block model as a whole, or for its individual zones bounded by a surface or a solid. And K-Mine has two options for sub-blocking. One is the regular one, which is bringing all the blocks to the same size, and another one is a irregular mode, which means that the minimum size of the blocks will be only on the border of the wireframe as a limiter, and the remaining blocks would be of different sizes. At the same time, users can change the overall dimension of the model and add new attributes. Many differences between the ore reserves estimation, grade control, mining and milling components of the reconciliation chain stem from the incorrect understanding of how geostatistical concept of block size, panel size, and selective mining unit relate to actual mining practices. So when we do estimations in mining applications, we often try to map the spatial distribution of the mineral attributes based on the block support rather than the sample support. The selective mining unit is the minimum support upon which decisions will be made, especially ore waste allocation decisions in open pit type of situations. The selective mining unit is usually smaller than the sampling grid dimensions, and especially at exploration and feasibility stages. This is why the direct linear estimation of these small blocks has a very low precision. So we will see how to reblock the model to increase block sizes. We select the original model with a block size of 30 by 30 by 7.5 meters and specify a new minimum block size of 120 by 120 by 15 meters. To recalculate the values of grades in blocks, we select the required one from the list of formulas, and it can be a weighted average by volume, weighted average by tonnage, or a value by maximum volume. We visualize only blocks in the graphite ores without host rocks and calculate volumes and average content. We'll see that the average graphite content in low-grade ore was 1.74%, and the average graphite content in high-grade ore was 4.83%. Now let's analyze the block model with the block sizes of 30 by 30 by 3.75 meters. We see that the total volume of high-grade ore has decreased from 86 million cubic meters to 62 million cubic meters. And at the same time, the average content of graphite in high-grade ore was 6.49%. So with underestimated value of the block size, we significantly underestimated the volume and tonnage while overestimating the average grade. So let's see an intermediate model between them with the block sizes of 60 by 60 by 7.5 meters. The values of volumes and average content are very close to the model with dimensions of 30 by 30 by 3.75 meters. And the use of the block model of the deposits makes it possible to calculate iteratively the volumes and quality indicators of ore grades and extraction units that were identified according to different options of the content of useful components. We see that for a model of a block size 120 by 120 by 15 meters, the intersection of curves of the grade tonnage graph at cutoff grade equals 3%. And now let's analyze the model with the block sizes 60 by 60 by 7.5 meters, and we see that interaction of the curves on the grade tonnage graphs is at cutoff grade equals 4%. So things that make it possible to quickly manage the resource base are a low degree of smoothing of grade variability with a regular and fairly dense network, combined with the use of cutoff grade in the block model as a condition parameter. This reduces risks and increases the profitability of the project without violating the principles rational use of subsoil. So you can also do a comparative analysis of the average contents in the original composites and blocks of the model, and also called swath plots. Using this report, you can identify areas of significant discrepancies based on interpolation results, and we can analyze the reasons for these differences. At some deposits, the planning of the mining operations in terms of the content of the useful component does not necessarily lead to the stable operation of the processing enterprise. That's happening because the commercial ore contains a charge of various technological grades, and this charge allows you to have a constant quality characteristics for the content of the useful component, but has sharply different technological properties. So based on working analytical relationships between ore concentration and ore quality indicators like content of useful components, the degree of oxidation of ores, fracturing, material composition, etc. So theoretically, geological and technological parameters can both be used in the block model of the deposit. Just in this case, you can determine the characteristics of the concentration of ores in each block. So you can also plan in the mining of the blocks with the necessary technological indicators, and you can check if there is a possibility of selective extraction of certain technological types and grades, and develop plans for extractions and storage of ore during the mining of individual sections of the deposit. You can also perform geometrization of ores that are equal or close in terms of technological characteristics, and finally you can just optimize ore enrichment, like adjust reagent regimes and etc. So this way, if you reasonably use mining and qualified maintenance of block geological and technological model data, you can quickly decide whether each next block of material should be mined and processed, mine and store, mine and sent to the dump, or as a host rock, or just not extracted at all. So here's the data that we will use to create an open pit optimization project. The block model dimension that was created and reviewed in today's demo are 60 by 60 by 7.5 meters. Mineral graphite, which is divided into 3 groups depending on the content, and the final product is graphite concentrate, the cost of which is $400 per ton. The cost of mining for graphite and overburden is $4 and $3 per ton, and we will set the enrichment in the range of $13 to $18 per ton depending on the content. The yield ratio also be correlated in the range of 4 to 8%, and cutoff grade will be taken at the level of 2%, as preliminary iterations have shown that under the given conditions, this is the optimal parameters that brings the most profit at the strategic planning stage. Well, we'll take the resulting angles from 35 to 45 degrees, which are distributed over the conditional zones. So let's proceed directly with the creation of this scenario. We will indicate the main information about the project, which is the name and location. Then we configure the display of output information in the settings menu. For tabular data, we will indicate the multiplicity equals 1 decimal place, and the multiplier is 1,000,000. So we will see the values in million tons, and to visualize wireframes, we will use previously prepared presets. The list of the horizons will be loaded from the previously prepared ones, and the height of each horizon is 15 meters, and the upper point is plus 150 meters, and the lower point is minus 350 meters. So next, let's add the block model, and we specify the attribute of the content of the useful component and the attribute of the class materials, which we will continue to work with. Then we will specify the volumetric weights of for rocks, and for rocks containing useful components, the corresponding attribute, and then we will activate the list of horizons. To indicate the resulting angles of the final contour of the pit, we will use wireframes, and for upper part of the formation, we will, since in most cases soft formations are present, the slope angle will be reduced. Also, conditionally, we will divide our field with 3 more wireframes: western, northern, and southern parts. So let's move on to completing the project. We will add 4 zones for each frame, and we will use filter that we prepared in advance. This filter specifies each specific wireframes for each individual case. So we are setting north for 45 degrees, south for 40 degrees, the overburden is 32 degrees, and for the rocks of the western side of the pit is 43 degrees. And we are setting the price adjustment coefficient in the range of from 0.5 to 1.2 in increments of 0.05. The cost of the final product will be set as $400 per ton. And we will set the cost of processing at the level of $13 to $18 per ton, depending on the content. Let's assume that the larger content is the cheaper the enrichment process costs us. So the cutoff grade is set at the level of 2%. So anything below this content will be considered overburden. The output coefficient will be set different from each type of rock. The lower the content is, the lower the output, and vice versa. It's like directly proportional relationship. And we will set the cost of mining operations associated with excavation and transportation at the level of $4 and $3 per ton for mineral and overburden respectively. Two parameters related to mining cost are set separately to make sure that we enter the most accurate information. The resulting value is represented by the sum of excavation and transportation costs. So we set the indicators of losses and impoverishment for rocks containing a useful component at the level of 10 and 5% respectively. So to calculate the net present value indicator, we'll set up a discount rate at 12% and the size of annual production at the level of 15 million tons. It really doesn't matter if you forgot to enter some data during the preparation of the project, because basically you can always return and complete the process. So let's set the resulting default angle for blocks that may not fall within the range limited by the wireframes as 42 degrees. We will make calculations and get instant results. We'll see that for the price adjustment coefficient, mining is not profitable. And let's see the sets of blocks that fall into each of the sets corresponding to the price adjustment factor. As you can see, with the increase in the coefficient, the number of blocks increases, which is logical since the cost of each block containing a useful component increases. So for coefficient, what coefficient is optimal for our artificial created conditions, we will try to, like, in order to answer this question, we would need to deal with the issue in more detail. Overall, in K-Mine software, the optimization models provide several options for analyzing the received information. The simplest and fastest are prepared charts that allow you to draw preliminary estimates and conclusions. For example, the differential graph shows the difference between the end shells of a pit, and as you can see, the maximum profitability is achieved with a coefficient numbered 7, which corresponds to a coefficient of 0.8, which happened because of the ratio of minerals and overburden. But even after this, significant increase in the mineral resource continues, and in order to extend the life of the enterprise, the coefficient is often adopted, after which a significant increase in the mineral resource ends. And until then, as a rule, the company can successfully operate and achieve the desired profitability. Alternatively, a pit with a coefficient of 1.05 can be taken as a final contour. And that corresponds to the number 12, and we will take it as the main one with which we will continue to work. So let's build a wireframe that will be based on the price adjustment factor of 1.05 for further use as a guideline. As you can see, the angles in the resulting pit differ depending on the geological zones indicated by us earlier. So in the next video, we will see the section where we will consider the several additional options for estimating the final contour, so we can choose the optimal one. The first example is based on the analysis of the wireframes. In some cases, it really has significant effect and shows optimization results from a different angle. For this analysis, we need to download the contours that of interest for us, which we would like to compare as wireframes. And by activating the visibility from the largest to the smallest, it's possible to track the growth of each subsequent contour in relation to the previous one. So next, let's build a section in order to visually evaluate the difference between the wireframes along the specific line. With the help of presets, the section will be built in seconds, and overall the setup just doesn't take long. We can see that longitudinal section shows significant changes between price adjustment frames, wireframes, and the farther to the east, the more significant it is. From this, we can conclude that the price of the final product significantly affects the final contours, and the choice of the optimal one must be treated with a margin, so we would leave reserved lands on the surface around the pit, since the pit can significantly expand if the price of the final product rises. For comparison, you can build also cross-section. Let's draw a line at the deepest point of the planned pit from north to south. And we will see that the northern part of the pit is more subject to changes than the southern one. It's worth keeping this information in mind when we make strategic decisions like planning communications on the surface of the pit. Also, going back to the resulting table, check out the fact that hidden lists contain a lot of information that can help with making decisions in a given situations. So if we need to analyze only the basic information, it's possible to just hide a more detailed description and export only the necessary information to Excel. As you can see, the information was transferred to Excel without inserted lists. And if we move on to the next analysis, we will analyze the marginal profit indicator. It is equal to the ratio of profit to expenses. This indicator is a percentage, and in some cases, the optimal open pit is considered to be the one whose marginal profits is closest to 20%. In our case, these are the coefficients 1.05 and 1.1 based on the results of the preliminary analysis. So remember that after the coefficient of 1.05, there is not a significant increase in the mineral. Judging by this indicator, the preliminary analysis showed a fairly accurate result. And now transferring data to Excel and not building the graphs, it would be a big mistake because the further analysis will depend on qualifications of the engineer that is doing it. So many graphs can be built with different dependencies depending on what needs to be analyzed and which indicators are the key. So finally, the best part we left for the dessert, and this is the functionality of the optimal pit model, which was expanded. And although it's still in the beta, we decided to show you these features. You will be able to see these updates in the next release. So let's make some settings first. We will indicate the coefficient that was chosen at the previous stages. It's 1.05 and try to create 3 pushbacks in automatic mode. We define the width of the working platform as 60 meters. The minimum area of the pushback is 20,000 square meters, and the minimum area of the bottom pit is 5,000 square meters. And the parameter responsible for the possibility of deepening is 120 ppm, which is per milli. Next, we set the target parameters for the search for the pushback, which are 3 equal parts by the amount of mineral in the final circuit, which is 60 million tons. Next, we will activate all available horizons. By the way, at this stage, we can limit the search for pushback by elevation. After that, we can start the calculation. It will take some time, and the more blocks in the block model, the search conditions and other parameters, the longer calculations will take. So let's see the results. The principle is the same, really, with the finite contours. We can display the blocks that got into the pushback and which is left after the removal of the pushback in the accumulative and differential modes. The search for pushback includes several critical criteria. The main ones being the optimality criterion, for example, optimal NPV, also a continuity criterion, and when we are working out the pushback, continuity must always be observed. Its connection must be at least ensured by the width of the working platform and other conditions that ensure the possibility of working out the pushback. In the event that the pushback that was obtained as a result of automatic search, if it doesn't satisfy any requirements, you can do also manual construction using guidelines or wireframes. Also, this method can be widely used if the enterprise has established or adopted a certain pushbacks over time. Adjusting them to the final contours is not difficult. You can also use the manual method of constructing the pushbacks in cases where automatic methods showed the direction, but let's say didn't cover the needs that cannot be entered in the model. In any case, the manual construction method can be used as a reference and as one that improves the automatic one. So let's see the contours on which our pushbacks will be based. It's 4 contours that were previously created, conventionally the center of the pit, south, north, and a separate part east. Let's specify similar parameters for manual construction. If the blocks are not defined in any of the pushbacks, they will be included in the separate one, which is indicated in the parameters. And we will not use height restrictions. We will only indicate the layer in which each of the restrictions will be stored for each individual pushback. In this menu, it's possible to take into account the pushback with angular dependencies when you are constructing the final contour, or you can include and exclude all the blocks that will be in this contour regardless of the dependencies. So in this case, the calculation will be made instantly since the set of the blocks has already been greatly simplified by establishing certain guidelines. So let's see the results of the lines. The blocks were assembled in accordance with the guiding contours, also taking into account angular dependencies. Blocks that did not fall into any pushback according to the criterion of minimal bottom area or another were discarded into a separate pushback. And we're going to create wireframes for each of the pushbacks to continue the planning process. And for the record, it is better to use different colors for each of the pushbacks. By visualizing each of the pushback in order from largest to smallest, we can observe the potential main sequence of the mining sections of the pit, which can and will be used in subsequent stages of planning. So let's get back to the modular data on the pushback. And we will see that all the necessary and interesting information can be found in the resulting tables for each of the pushbacks. Yeah, so this is the tabular data on the pushbacks. All right, so to sum up today's stream, we reviewed the cycles of creating key components of the digital environment and began the mine planning process. In the K-mine environment, we created block model, wireframes, populated the block model, and also got acquainted with the new features in the field of geology. And the second part, we considered the option of creating the optimization plan using the examples of graphite deposit in K-mine software, and also reviewed options for evaluating and choosing the final contour of a pit. And in conclusion, you saw the functionality of the optimization model in the field of pushback creations, which is the final stage of the development and will be available to users in the first quarter of 2023. So in the next stream, which will be a logical continuation of today's topic, we will look at the concept of mine planning again, using the latest model, which is automatic pit design, and we'll share with you some examples in more details. All right, so let's see if we have any questions here. And for the questions, I would like to include in our conversation our mining engineer Vitaly, who will answer your questions. Vitaly, are you here? I don't hear you.
Oh,
Now I can hear you.
cool.
Okay,
Mhm.
perfect. So the first question is if the mineral deposit is within wetland, river, or protected area, can the block model uh, plot those environmentally sensitive areas within the ore deposit?
Okay, so the answer will be it is possible to enter any text or numeric information into the block model. So it's just necessary to create a separate field which is this particular factor will be described. So, and after that, you can calculate this data and use these attributes to visualize your block model on the map, this part of the block model.
And if you would kind of like prioritize this mine planning process, what stage of mining process do you think is the most important?
Okay, so when we talk about some important things during the mining process, I'm sure that the most people think that, and they think right. I think that the most important process is life of mine planning, because during this process we usually try to resolve a lot of different uh, issues, a lot of different advantages we have to Mm, you have to fix. So, but by the way, all of the stages of the planning, they are all of them are really important. And what I would like to highlight here that that is not less even important that connection between these different stages of the planning because mm, um, when different departments create different plans and no any connections between them, it's no any like positive results, because so that's why the connection is a really important thing. And I think that it's really very important this plan reconciliation process, because after we create the plan, we try to follow this plan, but we don't know how much we have followed it. So we have to do this reconciliation and provide this information to the all planning departments. Yeah.
So, and what happens with the quality of the rocks when you do reblocking, and how it affects the accuracy of the model?
Okay, yeah, that's an interesting question. I was involved in some interesting communication with engineers and geologists, and geologist said, "Here is a block model. You can use it." And engineer take it, look on it, and he said, "Oh, I can't use it because for my modules I need to use a block model with a regular block size. Can you please reblock it?" And geologist said, "No way. If you will reblock it, you will lose the accuracy, you will not describe your ore body, you will lose in the important information." But engineer said, "I can't work with a regular block model, so please do something." And after that, geologist finally gave up and said, "Okay, I can do this for you, but don't show it to anyone." Because geology, just for geology, it's really interesting, but it should have some continuous. So of course, some part of information could be lost. So, and what about our reblocking methods in Kmine? So, you can make some transitions from smaller blocks to bigger blocks, and from bigger blocks to smaller blocks. So it's really a big difference between them. So when we trying to split the big blocks by smaller blocks, in this case, it nothing very exciting. So we will just expand this information from the biggest block to the small ones. But when we try to combine the smaller blocks into the bigger block, so here we have to decide what kind of information will we use to do that. So we can use in Kmine weighted average information by the volume. It will be recalculated. It could be recalculated by weighted average by the weight of this block. And in case if you would like to take into our consideration only the biggest block in this all of these blocks that should be combined. So we can take just average by biggest including block. Yeah, there is my
Okay,
answer.
we also thank you for your answering for the drama between geologists and engineers. Uh, well, we also have a question if this presentation will be available on PDF. This presentation will be available in recording video, so you will have access to that. Overall, we can also send you presentation about the specific bit optimization model, or you can just download it from our website. And the other question is, can the same process be done for the underground deposit? So for the underground deposit, it will be a separate model, and that will be available in 2023. So currently, this specific model is only for open pit. We will do the separate stream for the underground. Well, I think that's it. Thank you so much, everyone who joined in. Thank you, Vitaly. Don't forget to follow our LinkedIn page, and happy upcoming holidays, and hope to see you guys in 2023. Thank you so much.
Thank you. Goodbye.
Bye.